Hopefully you can see my screen here. I'm looking with you at notes today because I'm going to be absent. And you're going to do this lesson asynchronously and hopefully learn quite a bit about force along the way. So your job is going to be to make these notes yourself today, take good ones. I'm using a document that I posted several days ago in Google Classwork. It's called Forces Notes 2, and it has lots of space to do these problems. And you did this, I hope, already last time. And I left you with the challenge to go ahead and try using a system approach, because what we had done was look at two separate masses as if they were a single mass, because that gave us a little more problem-solving power. I'm going to also say that now that you're good enough at drawing sigmas and you're familiar with net force, you can start your formulas with either sigma F or jump straight to MA. If you do that, it might save you a line and some space and some time. You also can use W for weight, or you can use mg. That's perfectly okay in the AP world, including on the test. So just like last time, we still have the 8 kilogram and the 2 kilogram box together. So our system has 10 kilograms in it. So if I try for the net force of the system, I could do sigma F, or I can just start off MA. The only force on the outside pushing on the system is P, this pushing of 20 newtons of force. So we're looking at forces coming in from outside of the system in the case of a push. So when I substitute in the mass of 10 kilograms, it's really easy to see that the acceleration is once again 2 meters per second squared, just like it was over here. And that might lead us to believe that the normal contact force will be the same. So remember that a horizontal force here would be normal to this dividing line between the two boxes where they're in contact with each other. Contact means they're touching. So that force right there, the push, is normal to it. And it's a contact force because it only exists when the two of them touch. If they come apart, there's no more force. Okay, so we're trying to find the horizontal normal contact force. Okay, so let's see. I guess it's the 8 kilogram block that's being pushed by the 2 kilogram block. So I'm going to make a free body diagram of the 8 kilogram block. So I'll just name it 8. That's its name. So I have, as usual, weight down. That could be mg if I want to. And I have a normal up. And then I have the fact that the 2 is pushing on it from the left, which we draw like this. And we label it the force of 2, 8. The force of block 2 pushing on block 8. So now I'm going to go sigma F, or MA. And this time it's not the mass of the system. It's just for the 8 kilogram block. So I just want its mass times acceleration. And the only force on it, because they said friction is negligible, it is on this whole page, is this force of 2 pushing on 8, the normal contact force. So when I put in my 8 kilograms, and now I multiply by the acceleration of the system, because this 2 meters per second squared of acceleration has to be true for every part of it, because it's like a train. They're all hooked together. This one can't have a different acceleration if they're in contact with each other. So when I do that, I get my answer, which is the force of 2 pushing on 8, and it's equal to 16 newtons. That's quite different from last time. That little block of 2 has to push with a lot of force against that bigger mass with more inertia. So that's how you work system problems, and I'm glad you tried that challenge on your own. Let's try one more together. This one is pulling now, and we have something that really does look like a train or maybe a child's toy. There's a tension over here called T3, and we're told what it is. It's 24 newtons. But we're asked to find this tension, T1, and this tension, T2, because all three of these things are being pulled because they're connected by strings. So let's start off again finding it for the whole system. So if I take the whole system of mass, that's my big wide one now. That's 2 plus 4 plus 6. So that's 12 kilograms of mass. Okay, so I'm using this system approach again. It's also going to have weight down, and it's going to have a normal force up. Sorry, I'm kind of messing up my drawing there with the word system. And it's got T3 pulling on it. I won't call it P or applied force because I was given a name for it in the problem. So when I work just on that, I'm going to see if I can find the acceleration of the system. So the only horizontal force is T3 because friction is negligible. So when I sum the forces, sigma F or M system A, system, is just a very short list. It's T3. So if I put in my 12 kilograms, I can solve for A. There's the 24 newtons of tension I was given right there. So in this case, interestingly enough, just coincidence, I get another acceleration of 2 meters per second squared. That's the acceleration of the system, but that also means it has to be the acceleration of every part because they're tied together. They can't just take off by themselves. So now I'm going to start working to find these other tensions. So let's start off and see if we can find T1. So the sum of all forces on T1 is going to come from this little tiny free body diagram right here, where I have a force called T1, I have weight down, I have normal up, and that's all I have. So that thing is clearly going to accelerate to the right. So now I can go, okay, that means net force or mass times acceleration on the 2 kilogram block will equal the force we're calling T1. So I'm going to put in 2 kilograms and I'm going to multiply times the acceleration of the system that we found over there. It's just off camera, right? It's 2. So now I multiply times 2 meters per second squared, and I can see that T1 is 4 newtons. So I found one of my answers already. Okay, let's try another one. Let's try the 4 kilogram block. In the case of the 4 kilogram block, I have a force pulling on it called T2. But I want you to think hard about this. How much mass is there really if I'm looking at what T2 is doing? T2 is not pulling only the 4 kilogram block. It's actually pulling 6 kilograms. So when I try to figure out this, I need to think about the total mass that this T2 is pulling on. Again, I have no friction, I'm just working with horizontal forces. So this time my mass is 2 plus 4, okay? So working on T2, I've got to take into consideration 4 kilograms of mass times 2 meters per second squared, the acceleration of the system. Okay, oh, I'm sorry, I wrote that wrong. It's 4 plus 2, so this is 6, right? I have 6 kilograms of mass times that. Acceleration of the system. So that means T2 here is going to equal 12 newtons. Sorry, that's so ugly. But that is 6 times 2, that is 12 newtons for T2. Okay, T3 we didn't have to find because they gave it to us. So you might think we're done. But I want you to look at this another way. I want you to think about what it means when we say directly proportional. Directly proportional. And I want us to think about it in light of Newton's second law of motion. It says that acceleration is directly proportional to the net force and inversely proportional to the mass. So in other words, the bigger the mass, the smaller the acceleration. Or if you prefer to write it this way, the bigger the acceleration, the bigger the force. But look also, the bigger the mass, the more force it's going to take to cause the acceleration. So let's revisit each of these. Let's think about it in terms of mass. What proportion of mass is this little block? Okay, so let's revisit T1. So I'm going to ignore that one over there and just say T1. T1 is 2 kilograms divided by a total mass of 2 plus 4 is 6, plus 6 more is 12. It's 2/12 of the total mass. So in other words, it is 1/6 of the total mass. If it's 1/6 of the mass, it's going to take 1/6 of the force to accelerate it. Okay, so 1/6 of force is 1/6 of means multiply, 24 newtons. This is a whole nother way to get it. Okay, just looking at proportions, I can see that that has to be 4 newtons of the 24 newtons. Let's try that approach again on T2. We said T2 was 12 newtons. Let's look at it in terms of being proportional. How much mass is T2 pulling? T2 pulls 6/12 of the mass. Therefore, T12 is going to require 6/12 or 1/2 of the force in order to move that sort of second half of our train. So uses, if you want to think of it that way, 1/2 or 6/12 of the 24 newtons. So 6/12 of 24 newtons is 12 newtons. It's half of it. So look there, we're checking our work. So, and of course the 24 Newton force is pulling all of them. And that's how we got our acceleration of 2. So there's a lot to be seen when you work with systems. So I hope you try that and practice it. This first question, remember, is fair game for the quiz that we're going to have next class on Wednesday, but nothing after that, okay? Because we did that one last week, or you should have done it from Friday's lesson. And so what's below is on a future quiz or test, not on this one. Okay, here's a really interesting system. A man named George Atwood asked a very interesting question. He said, which way does gravity pull? Let's say it pulls down. What if I had two things gravity was pulling on? And what if I connected them by a string and put them over a pulley? Can you see a pulley? A pulley is a wheel that turns freely. Oftentimes you see a star or something like that with spokes going out. So if you ever see something like that, that's a symbol for a pulley. So you can see he'd have to haul this up, because I think you agree the big one would fall down and the littler one would rise up. So he would haul it up like this and hold it still, and then he'd let it go. And he asked the question, what would the acceleration be? Would it be 9.8? Would it be half of 9.8? What would it be? And he worked out experimentally. I got a bunch of results and figured out, I think I see what's going on, and here's how we diagram those forces. Okay, so I'm going to teach you how to solve an Atwood machine problem. There's a lot of complexity here, and this one often shows up on AP exams and often shows up on our force test in the fall here at Reagan High School. So let's see how we do this. In the previous example, we were taking objects that were tied together and are touching each other and treating them like one mass. In this example, we really need good free body diagrams, as in free. So we're going to make two different diagrams. I'm going to bring the small one over here, and I'm going to use S for small this time. So not system, but small. Okay. And when I look at that, I'm going to think about the forces on it. It has only two forces on it. It has its own weight, which you can call WS or maybe MSG. And then it has tension pulling up on it. So I'm just going to put tension. I have to think a minute about whether that tension needs a subscript. But those are the only two forces acting on that mass. This, by the way, is the origin of the elevator. This is how the elevator was invented, based on George Atwood's work. Okay, so I have the big one over here. So let's use S for small and B for big, and I'm going to go way left over here so that we have room, because this is going to be kind of a space hog of a problem. You may have been wondering why I left so much blank space. You'll see soon. So over here, I have the weight of the big one pulling down. I definitely need a subscript because this is the weight of the big one. So maybe MBG would be okay too. And this tension's going up. Now, I'll tell you right now that the reason you use a pulley is because it makes the tension equal. Okay, so assuming it's a good pulley, it's not all rusty and stuck, the tension in the string is going to be everywhere the same. So that tension and this tension, they're the same in magnitude, and they don't need anything like subscripts. We could use like the conventional direction here of up is positive and down is negative, or maybe we couldn't. You don't want to. Let me show you why. Which way is gravity pulling? Gravity pulls down. Okay, so this is going to be my model for the string. Remember, a model is just a simplification that helps us understand. So that's the string that connects the two masses. So on this end, I've written weight down to show the direction of gravity. And on this end, I've written weight down to show the direction of gravity. Okay, so down is down, unless it's like this tied over a pulley. Do you see that those two weight vectors are actually pulling in opposite directions? Look at that again, they are. Both of those downs are in a tug of war. They are pulling in opposite directions. Okay, what's happening with tension? Well, both of those ups are also pulling in opposite directions. Let me use my fingers this time. If this one's up on the small mass and this one's up on the big mass, if I sort of pull those masses apart and straighten those out, can you see they're opposing each other? So a system of up is positive and down is negative does not work when you have something rolling in a circle like this pulley. So George Atwood established a convention we call the Atwood Convention. It's so useful and so often used in physics. And he said, let the positive direction be the direction in which things actually move. Well, let's see, if the big one's going to fall down and the little one's going to come up, anything that helps that happen is going to be positive. So counterclockwise is another term for how it would look in this situation. And anything that fights that is going to be negative. Okay, so now we've got a system of signs. Is this WS positive or negative? Is this WB positive or negative? Well, this downward vector is definitely causing this big one to come down. That's in the positive direction of motion. That thing is a positive force vector. What's fighting it? The lift of this tension is tending to oppose that. Okay, what is this tension doing? It's helping the little one come up and the big one go down. So that means that's a positive tension. Okay, and this weight pulling down on the small one is fighting the positive direction of motion, so that's going to be negative. One of the nice things about doing this on video is you can stop and replay, and I hope you take full advantage of that. You can also watch it another day because this is pretty complex stuff. But that system of signs, I hope, will become familiar to you. Just however things are going to move, let that be your positive direction. So let's try our free body diagram turning into a net force statement now. So if you want to, you can start straight off with MA, or you can do sigma F. But this is going to be net force on the smaller block or smaller mass. And that's equal to tension up and weight down in the negative sense. And it's the weight of the small one. So I'm going to go mass times acceleration, small mass times the acceleration. Is that just the acceleration of the small mass? No, I think they're going to be the same. That is, there's a system tied together here. Whatever this has for an acceleration, this one has also, because they're tied, they can't get apart. So I don't have to have a subscript for that. So this is just tension minus mg. And now I think I'm kind of stuck. Believe it or not, we know the masses. I need to put an S there, by the way, because they told us small mass and big mass. What we don't know is A and T. We know G is 9.8, but we're kind of stuck here. We could make everything positive if we wanted to, like we could add an MGS to both sides. So let's do that, I guess. M small g got added to both sides. So this is M small g plus M small a. That was originally already on the left side. And I left the equal sign and the tension right where they were, but I'm stuck. What do you do when you have one equation and two variables? Do you hide under your bed? No, you're an upperclassman at Reagan High School. Do you cry for your mom and suck your thumb? No, you know better than that. You know you need to go looking for a second equation. Look, there's going to be one right there, right? No fear, right? One equation, two variables, no fear. Two unknowns, no fear. Okay, let's try it. The sum of all forces on the bigger mass is equal to the tension pulling up, negative direction, and the weight pulling down. Keep the subscript. We need to know that's the B. Notice that down is positive. It's helping the positive direction move. So this is mass B times acceleration of the whole system as well as of B equals negative tension plus, what do we put in for weight? Oh yeah, mg. Using subscripts because I have two different masses otherwise. I don't know, I guess I could make that negative tension positive. I think I will actually. I'm going to add a positive tension to both sides so it moves over here. So what it's left behind is mbg. That was originally on the right. But I'm also going to subtract mba, because I think I'm starting to see how I want to work this. I have tension over here, and I have tension over here. Each equation has the same two unknown variables. So I hope you can see that if I set them equal to each other, if I say tension equals tension, I'll be able to get rid of that tension. Because instead of tension, I'm going to write mbg minus mba. Okay, the result of our work with net force on the left using the free body diagram for the big mass equals, right here, msg plus msa. The result of our work with the free body diagram and the net force equation for the small mass on the right. Now, I have A's in two places, here and here. And that's the only unknown I have, okay? Because we know the masses, we'll say. So that means what I should do is try to collect all the A's on the same side of the equation. I think I'll put them on the side that makes things positive. So I'm going to add an MBA to both sides of the equation. I'll just write it on one side if that's okay. So that means this side over here is going to have an MSA plus an MBA, okay? But at the same time, I think I want to get all the regular numbers, you know, the numbers that don't have an A, I'll put them over here. So in the same step, I'm going to subtract MSG from both sides of the equation. So what will I have when I do that? The left side will be M big G, in other words, the weight of the big block, minus this thing, MSG, in other words, the weight of the little block. So the left-hand side is now showing me the difference in the weights. Oops, sorry, light sensitive. On the right-hand side, this is gone, but I'm adding MBA to both sides. So this will be mass big A plus mass small a. Next step, trying to solve for A. Remember, they said find the tension in the string and the acceleration of the system. Oh, hey, do you realize we already did half the problem? We've got tension. Look, I have an expression for tension right there. And there's another one right there. So now what I have to do is clean this up a little bit so I have an expression for the acceleration of the system. So let's factor out an A. When I do that, this becomes big mass plus small mass. Over on this side, let's just factor out a G too, since we're using parentheses. This becomes, instead of the difference in the weights, it looks like inside the parentheses, I can see the difference in the masses. And I'm starting to see Newton's second law of motion. Can you see it? Newton's second law of motion says A is equal to, the acceleration is equal to the net force divided by the mass. Why is this thing moving? That's another way to look at it. Why would this move at all? What's the driving force that's making it move? The answer is right here. It's the difference in the weights. You see that difference in the weights? That's why it would accelerate at all. So now if I solve for A, I'm going to divide both sides by this parenthesis. Okay? So A will equal the difference in the masses, or actually the weights, because I don't think it would accelerate on the International Space Station where it might seem like there's zero gravity, divided by this parentheses, the total mass. Now can you see Newton's second law? Total sluggishness, there's the mass right there. Net force, the reason why it moves is the difference in the weights. Think about net a minute. When you were a cute little kid, you were 7 years old, maybe you had a lemonade stand. Your parents were nice and they went to H-E-B or someplace and they bought lemons and sugar and cups for you, or maybe they bought Kool-Aid powder and cups for you. And then they spent, like, let's say they spent $12 on that, and ice. So then the next day you're out there on the street corner selling your lemonade for $1 a cup. And you're so cute that you immediately sell like 20 cups and you go running into the house going, Mom, Dad, I made 20 bucks. You didn't net 20 bucks. Your parents didn't know. I mean, you didn't know that, but you had $20 of profit, but your parents had already spent $12. So what was the net? The net is the difference between the two of them, right? It's what you had to do to cover your losses first. It's what's left over. So this is what we have left over, if you will, to cause acceleration. The difference in the weights. The other expression you might want to think about is the driving force. I don't know if you know that expression in English, but it means the big reason. What is the driving force behind why you're doing so much homework at Reagan? Maybe because you really want to get into that college of your choice. That's your driving force, okay? So this is the driving force, the total, well, the difference in the weights. And this thing right here is the total sluggishness, okay? So the driving force divided by the sluggishness. Sluggishness, I don't even know if that's an English word, but that's the inertia, right? That's what we have right here. So another way to look at Newton's second law is why would something accelerate? Net force. Divided by why would it not accelerate? Lots of mass is sluggish. Okay, so here's our expression right there, coming from Atwood machines and George Atwood's work, that will tell us the acceleration. Okay, complex problem. Keep in mind, you can come back and view this again. We have a problem to do underneath that's numerical, and we might be able to take advantage of the fact that we've already done all this work. We have tension equations and an acceleration equation. And now we're asked specifically what happens if these are the masses that are used. So solve this for a 2 kilogram mass tied by a string over a pulley to a 4 kilogram mass. Okay, I can do that. So A equals mass big minus mass small times G, right? Just thinking about it for practice. The difference in the masses is the difference in the weights. And then I have to tally up the total mass because that would be the sluggishness. Okay, that's easy enough. So this would be, I don't know, do you want to work right or do you want to work down? I guess I'll work right this time. So this would be mass big is 4 kilograms. You can leave the units out. Minus mass small is 2 kilograms. Okay. Times 9.8, because it's not just the difference in the masses. Planet has to be pulling on them, right? Times 4 kilograms plus 2 kilograms. Okay. So grab a calculator. And this point, I'd like you to hit pause. I'm going to hit pause too. So if I just pause the recording for just a moment, that might give you an opportunity to, okay, hopefully you're not playing on until you've solved that yourself. So here's what I got. Did you get 3.27? I did. I got 3.27. Now that's going to be an acceleration, so that's in meters per second squared. Okay? There's a lot of work there. What if I did that wrong? And by the way, you might be asking this question yourself right now. Ms. Bolster, are you going to make us do all of this on the test, or are you going to let us just do this? You don't know. And frankly, that's because you don't know in May either. I haven't even decided at this point. But I can tell you that often in the past, I have asked for the full deal. So if it says an Atwood problem and it just gives you numbers and you've got this memorized, or you can reason it out like y over and y naught, you can just jump right to the calculations. But if it says draw net force equations, write net force statements, and derive an expression for the acceleration and the tension in the string, you're going to have to do all of this. Okay? But for right now, we're just going to go with a numerical solution. How do I know that's right? And by the way, I should try to find the tension. Wait, I have 2 tensions. How do I know which one to use? Well, this is what's really cool. That will provide a way to check all of your work. So let's try that tension equation up there. It says mass big G minus mass big small, minus mass big A. So tension equals mass big G minus mass big A will look like 4 kilograms times 9.8 meters per second squared minus 4 kilograms times that number. Only please use the unrounded number that's still sitting in your calculator. So let me pause a minute while you do that. You can hit the pause button if you want to, that would be great. So just pause a minute, please. Got it? Okay, here's what I got. I got 26. So my calculator says there's 26.1 newtons of tension, because tension is a force, in that string. Is that a reasonable number? Yeah, because I'm like, 665 newtons or something like that. So that's pretty small, and that would be maybe appropriate for a string. But here's how you check your work. You've got 2 tension equations up there, right? Let's try that other tension equation. That other tension equation says tension is also the small mass's weight plus MSA, the net force on the small mass, right? So this is going to be 2 times 9.8. So that's 19.6, right? And this is 2 kilograms times my best unrounded number for the acceleration of the system. So hit pause if you want to and try that, or I'll just go slowly. Maybe that'll work. And I got the same thing again. Did you? So this is how you can check your work on an Atwood problem. There is only a single tension in the string. So if you get a different number here, then something's wrong. Probably your acceleration is wrong, okay? And you need to look at everything again. So it's really nice if you have a way to check your work. Okay, so what have you done today? Well, you practice working with systems where you treat them first as a single unit of mass to get a piece of information that then lets you work on them independently. You looked at how direct proportionality can be used in kind of a shortcut. Because remember, a lot of your questions, half of your questions on the AP exam are going to be multiple choice. So you don't always have to do everything here with free body diagrams. It's possible to develop kind of an intuitive sense about acceleration and force and mass. And here we've learned how to solve an Atwood problem. We've learned what the Atwood convention is, and you've practiced your algebra skills, I hope, because this is the language of physics. And we want you to be able to speak that language really, really well in May. Okay? So to get asynchronous credit for today's work, you take your own notes written in your own handwriting and take a scan of those and upload those into Google Classroom as just one document. Okay, so try that technique where you're scanning. Remember I hope you learned how to do that. I mentioned it at the end of the Friction Lab. So you're scanning 2 pages into one document, okay? And when I find that there with today's date on it, that will be your asynchronous credit for the day. So thank you very much. It's good to see you. See you again in person soon.